WP 3 is about the simulation environment in this project and how to set up the simulation. In WP 3 we are gathering a lot of data from the real systems, and we are using our simulation environment with the real data and the models we get from Work Package 2 in a standardized way, and we have performed the following results.
In SPEAR, we target to use energy models of components provided by standard way to get energy consumption and power flow of the components based on a simulation instead of real measurements. To do this, we need a simulation environment which allows us to run simulation during the design phase, virtual commissioning, as well as during the real process. To achieve this, in SPEAR we focus on energy models based on standard like Automation ML and Functional Mockup Interface. As a result, we developed a simulation environment based on an existing FMI library without any external requirements to other tools. For this, we create an adapter as a FMU which connects the simulation environment to the EKS shared memory concept. With this, we can connect the existing tools ABB read to get signals from the real robot controllers, as well as FSBox to get signals from real PLC. Additionally, we create an adapter to connect simulation environment, for example on several single board computers with ROS and shared memory. With this, a scalability of the simulation is achieved. Use of such single board computers are required to prevent higher hardware costs in case of running the simulation environment during the real process. The simulation environment creates energy profiles of each component based on different process parameters, for example, the speed of a robot for the same robot program. All profiles are uploaded to the optimization platform via the SPEAR interface description. Here, the simulation environment is shown in case of a virtual commissioning. Thereby, the air flow and air consumption is calculated. As next, a virtual commissioning setup of a body-in-white production system is shown. Thereby, the energy consumption is calculated in ABB Robot Studio and used for subsequent energy analysis and optimization. This example shows the simulation of AGV with the existing tool NX extended by the cost simulation from the ITEA project NTOC. During this, the energy and power profiles are calculated based on the FMU of the AGV energy model. This example shows that the SPEAR approach can also be used to define the AGV path in the design phase, taking into account the energy consumption. The next demonstrates the possibility to optimize energy consumption of industrial robots through minimize the acceleration and speed and scheduling of process tasks sequence by keeping the same move path and target cycle time. Thanks to this, the energy consumption of shown robot was reduced by approximately 25%. With the next example, the robot motion are analyzed and optimized based on a simulation as well as real data from controller. Thereby, the speed commands of the robots was included into the optimization by the same cycle time. Thanks to this, waiting times can be prevented. With this result of SPEAR, an energy optimization was achieved about 12%. The following shows the distributed simulation environment on a single board computer architecture.
This is a quick demonstration of a simulation setup using Raspberry Pi for simulation node. Using the dashboard, we load up a configuration file to modify and send the configuration to a Raspberry Pi node. This setup is done via Wi-Fi connection. And here we can see one of the two Raspberry Pi nodes that are used in this setup. The monitor shows the values that get propagated between the two Raspberry Pi nodes and the master computer. The Raspberry Pis do not need to have any screen or input-output devices connected to them. It's all controllable via the master's dashboard. The dashboard also gives us the ability to see the Raspberry Pi's output. You can select any simulation node that provides an output, and the dashboard will plot the data for you. The plots are done with a refresh rate of 5 Hz, but the simulation can run up to about 100 Hz.
All these results were achieved thanks to the SPEAR project, and we would like to thank ITEA, BMBF and Vinova.